In today's lesson, we will be focusing on sequences and series, and the objective is that students will be able to determine the sums of arithmetic and geometric sequences, and they will be able to determine limits of partial sums and the convergence of geometric series. All right, we started out by taking a look at that activator, which focused on the sum of a sequence. All right, and you were given a problem where you were asked to determine the sum of 100 consecutive numbers, and if you could potentially come up with a strategy for solving that problem. One of the ways in which we could do that is if we think about the different numbers, we could kind of group them into two groups. We have the numbers 1 to 50. All right, we have the numbers 1 through 50. And we have the numbers 51 through 100. So I can think of 100 through 51. And if we were to line them up like this, in this order, the way I have it written, we could say, 100 plus 1, that gives me 101. 50, 1, and 50 gives me 101. Well, 99 and 2 is also 101. And we would have 50 of those 101s, or it would just be 50 times 101, which would give us 5,050. And so just like that, I was able to determine the sum of the first 100 terms. Now we could think about it for 10, the same thing would apply. It would be 5 groups of 11, or 5 times 11 would get me 55, which is what we got there. Because we could do 1 and 10 makes 11, 2 and 9, 3 and 8, etc. And we would find that each pair adds to 11, and there would be 5 of those pairs. So that was one way in which you might have thought of finding that sum more efficiently. Well, going back to the lesson here, we're going to learn about summation notation. We're going to learn about the sum of an arithmetic sequence and the sum of geometric sequences. And then we're going to look at something called infinite series and convergence. All right? And that's what we'll be focusing on today. So let's start with summation notation. All right? In summation notation, the sum of the terms of the sequence a sub 1, 2, 3, all the way to a sub n is denoted as capital sigma. So this is a capital sigma, and that's what we use for summation. So this is the summation of all the numbers from k is 1 to n of a sub k. All right, so this is read. We literally read this right here as the sum of a sub k from k equals 1 to n. The variable k is what we call the index of summation. It just tells us we're going to start with 1, 2, 3. So whatever you put on the bottom tells you where to begin. And n tells you what the last value for k should be. And we go through one at a time, and we add all of the components. So let's take a look at this exploration here at the bottom of the screen. So what I would like you to do is I would like you to start with the first one. We'll do this one together, and then I'm going to have you do 2 through 5 on your own. All right, so for the first one, we're saying the sum of 3k from k equals 1 to 5. So it would be 3 times 1, which is 3, plus 3 times 2, which is 6, plus 3 times 3, which is 9, plus 3 times 4, which is 12, plus 3 times 5, which is 15. And we're just going to get the sum of these values. So we get 9 plus 9 is 18, plus 12 is 30, so that gives me 45. And so just like that, I'm able to determine the sum of 3k from k equals 1 to 5 is going to equal 45. Notice how we have k in our summation there. That's really important because as k changes, the value that we're adding is going to typically change each time through. All right, so go ahead and take a look at 2, 3, 4, 5, and see if you can come up with the sums for each of those terms. Pause your video, and we'll go over the last 4 when you come back. All right, welcome back. You should have had a chance to go ahead and attempt to find the sums for each of these different terms here. So the second one, we have the sum of k squared from k equals 5 through 8. Well, when k is 5, we get 25, plus when k is 6, we get 36. When k is 7, we get 49. When k is 8, we get 64. And we would sum all of these together. We end up with 149, 59, 69, 174. All right, and that's what you should have gotten for the second one, 174. So all we're doing is we're plugging in 5, 6, 7, and 8 into k squared and adding all of the results together. All right. For the third one, the sum from n is 0 to 12 of cosine of n times pi. Now, if we think about cosine, all right, if we think about our cosine function, all right, we're going to start out at 0 pi or 0. That's when cosine is equal to 1, right? If we think about our graph for cosine, right, we have 1, it's 0 at pi over 2. At pi, it's going to be negative 1, right? Back to 0, back to 1. So every pi, so this is kind of interesting. We're going to essentially say for number 3, when n is 0, right, it's just the cosine of 0, which gives me 1. When n is 1, it's going to give me negative 1. Back to 1, back to negative 1. So it's 1, negative 1, 1, negative 1. And we're going from 0 to 12. All right? So 0 and 1 just cancel out, right? So 0, 1 cancel out, 2 and 3 cancel out, 3 and 4, 10 and 11 will cancel out, and we'll just be left with 12. So finally at the end, we're going to add 1 at the end, and our sum is just going to equal 1. If we were looking at sine, it's a very similar type problem where we're going like this, but each time through, at each interval of pi, we're just 0. So we're adding 0 plus 0 plus 0 plus 0 plus 0 plus 0. It ends up being just 0. The last one is interesting, and it says here, if you're having trouble with number 5, try writing the sum as a decimal. All right, so if we think about it, when k is 1, it would just be 3 over 10, which is 0.3. So then we're going to add 3 over 100, which is 0.03. So when I add those two, we get 0.33. The next one, we're going to add 3 over 1,000, which gives another 3, another 3, another 3, etc. forever, right, all the way to infinity. So our decimal would be 0.33333 repeated, which is the same thing as just saying 1/3. All right, so you should be able to go through and see what we can do with these summations and how those summations work. But most importantly, you should be able to read a summation and understand exactly what it's talking about, understand what it is adding together and how we would come up with that summation. So here we're going to take a look at a theorem for the sum of a finite arithmetic sequence. So if we let the sequence be a sub 1 to all the way to a sub n be a finite arithmetic sequence with a common difference d, then the sum of the terms in the sequence of the sum of a sub k from k is 1 to n is just going to equal a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n, which is the same thing as saying n times a sub 1 plus a sub n over 2. This is exactly what we did on that summation from 1 to 100. We took 1 plus 100, got 101, divided it by 2, and that gave us 50.5, and we multiplied it times 100, and it gave us 5,050. So this is the same thing as n over 2 times a sub 1 plus n minus 1 times d. All right, this is how we would find the sum of an arithmetic sequence. So let's apply what we just learned to finding the sum of an arithmetic sequence. So if we had a corner section of a stadium, all right, so we're thinking, think about maybe a football stadium or some kind of stadium, all right, the stadium tends to be kind of an oval like this, and we're looking up in the upper corner section. You have some section that's like this, and the first row here has 8 seats. The top row here has 24 seats. And the next row is 10, 12, all the way up until the top has 24. All right, so we can kind of think of a section like this. And we're going 8 seats, 10 seats, 12 seats, all the way up to 24. 16, 18, 20, 22, 24, and I want to know what's the total number of seats in that entire section. All right, well, this is just the summation of the number of seats from the first row to the last row. All right, so the way in which we would actually write this out, we could know that the first term is 8, and I know that a sub n is 24, and I know the change is 2. All right, and if we know that, this is very, very simple because we had that original definition that we could just say that it's a sub 1 plus a sub n divided by 2 times n. The problem is we don't necessarily know what n would be unless we know how many rows there were, which we could count out. So let's go through and let's solve this out using a sub n as the first term plus n minus 1 times d. Well, we know that a sub n is 24. We know that a sub 1 is 8. And so now we need to solve for n. This is going to tell us how many rows there are. We plug it in, we do just a little bit of algebra solving for n, and we find out that there are 9 rows. Now, could I have just counted? Of course I could have. But if it were a scenario where there was a much larger number or something, you might not want to do that. We could just use the formula to solve for n. Then we just plug it into the theorem that we learned about, and we do 9 times 8 plus 24 all divided by 2, and we find that there are 144 seats. All right, and we can also compute the sum on a calculator. You can actually plug in the sum of the sequence of 8 plus n minus 1 times 2, where n goes from 1 to 9. This is kind of the syntax for what you would write in your calculator. That's not something that you really should need to do. Just plug it into the formula for the theorem, and that should. So let's take a look at how we would find the sum of a geometric sequence. So the theorem here is that for that sequence, a sub 1, 2, 3, all the way to a sub n being a finite geometric sequence with a common ratio where the ratio does not equal 1, then the sum of the terms in the sequence can be defined as the sum of a sub k from k to equals 1 to n is going to be a sub 1 plus a sub 2 all the way to a sub n, which equals the first term, a sub 1, times 1 minus that common ratio raised to the nth power, all divided by 1 minus the common ratio. All right, so if we were asked to find the sum of this geometric sequence, 4, negative 4/3, 4/9, etc., we would find that the common ratio here is negative 1/3. R is going to equal negative 1 over 3. This is what's going to be multiplied every single time. All right, so that's R. So if I'm trying to find the sequence from 4 all the way through the final term, 4 times negative 1/3 to the 10th, well, if we think about it, the first number, 4 times negative 1/3 to the 0, gives me 4. So that's my first term. The exponent would be 0 all the way to the exponent 11. This tells me that n is going to equal 11. So I know that n is 11. My ratio is negative 1/3. Now that I have that and I know that my first term is 4, I can just plug everything into here. It's just going to be 4 times 1 minus negative 1/3, all raised to the n, where n is 11, all divided by 1 minus a negative 1/3. All right, and when we actually go ahead and do that, we end up getting this number here, which is 3.000016935. All right, which is going to be the sum of that sequence. So we're just going to use this formula right here that we've circled for finding the sum of a geometric sequence. So now we're going to go ahead and we're going to take a look at what we call an infinite series. All right, an infinite series is an expression of the form of the sum of a sub n from 1 to infinity of a sub 1, a sub 2, all the way to a sub n. Now the big thing about this that makes it different than what we've been looking at before is that it is not a true sum. All right, there are properties of real number addition that allow us to extend the definition of a plus b to sums like a plus b plus c plus d, e, f, but not to infinite sums, right? This goes on and on to infinity. There's an infinite number of terms, all right? So we can add any finite number of 2's together and get a real number. But if we add an infinite number, we do not get a real number at all. Sums do not behave that way. So what makes series interesting is that sometimes the sequence of partial sums, all of which are true sums, approaches a finite limit. So we could say we want to find the limit as n approaches infinity of the sum of a sub k from 1 to n, all right, which gives us a value which is the limit as n approaches infinity of a sub 1 plus a sub 2 plus a sub 3 dot 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 all the way to a sub n is going to equal some value s. All right. So in this case, we would say that the series converges to s, and it would make sense to define s as the sum of the infinite series. So we would say that the sum of a sub k from 1 to infinity is equal to the limit as n approaches infinity of a sub k from k equals 1 to n. And we would say that that equals some value where it converges. So if the partial limit sums does not exist, then we would say the series diverges and it has no sum. But it's quite possible that at the limit as n approaches infinity, all right, it will converge at some value, which we would call s. So we can take a look at limits of partial sums. So in each of these series, we could say find the first 5 terms in the sequence of partial sums and which ones appear to converge. All right. So let's take a look at A, B, and C. The first one, 0.1 plus 0.01 plus 0.001 plus 0.0001, and we see the pattern, right? We're adding, so it's a tenth and a hundredth and a 1,000th, a 10,000th. This appears to go to, all right, in the long term when we add them together, it's just going to be a decimal point with all ones, all right, which approaches the value of 1 over 9. The second one is just getting bigger and bigger and bigger and bigger and bigger. This approaches infinity. It does not converge. It diverges. 1 minus 1 plus 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 1 minus 1 kind of bounces back and forth between 0 and 1. So what would we say? Well, the first one, it approaches the limit of 0.1 repeated, which is 1/9. It suggests that the series converges to the sum of 1/9. The second one, it's increasing, does not approach a limit, it diverges. And the last one, they oscillate and don't approach a limit. Therefore, it diverges and has no sum. But the first one did appear to have that sum, and we would say that the series converges at 1 over 9. All right, we can also look for a convergence of geometric series. All right, and we can determine the convergence or divergence of infinite series. And this is an important part of a calculus course in which series are used to represent functions. So most of the convergence tests are well beyond what we're going to look at, but we're in a position to settle the issue completely for geometric series. So geometric series we can actually know for sure. And we would say that a geometric series, from k equals 1 to infinity of a times r, which is the rate to the k minus 1, converges if and only if the absolute value of r is less than 1. If that rate is not between -1 and 1, right? The absolute value has to be less than 1, and if it is, then it will converge. And the sum is just going to be that first term a divided by 1 minus r. If the rate is 1 or larger, or the absolute value is greater than or equal to 1, then it's not going to converge. So we're going to say we want to determine whether or not the series converges. And if it does, give the sum. Well, in the first one, what is r? R here, the rate is 0.75. The absolute value of 0.75 is in fact less than 1. So this one we're going to say it does converge. We'll take a look at the sum in a minute. The absolute value of -4/5 is less than 1. It's going to converge. Pi over 2 is greater than 1. So this is divergent. 1 plus 1/2 plus 1/4, etc. Well, what is the rate here? The rate here appears to be 1/2. We're getting half. So that one is also going to converge. So we'll go ahead and we'll take a look at A, B, and D. So in A, we're just going to plug that in. We're going to do, we'll find the first term, which is 3. And so the sum is just going to be that first term A divided by 1 minus R. So it's 3 divided by 1 minus 0.75, which gives us 12. We do the same thing for B. We find the first term. It's 1. So it's just going to be 1 divided by 1 minus a -4/5, gives us 5/9. C, we know it diverges. And then the last one, we know it converges. The first term is 1, so the sum is just 1 over 1 minus 1/2, which is equal to 2. All right, so we can find the sum of an infinite geometric series. That's something that we can do, and this will always work so long as the absolute value of r is less than 1. All right, so one of the applications of the sum of a geometric series is that we can convert a repeating decimal to fraction form. So if I wanted to express the decimal 0.234 repeating into fraction form, I could use the convergence of a geometric series. So we can rewrite this as a sum of 0.234 plus 0.000234 plus 0.0000000234, etc. All right, so this would be an infinite geometric series in which A is 0.234 and R is 0.001. So we know that the sum is just A over 1 minus R, which is 2.34 over 1 minus 0.001, which is 0.234 divided by 0.999, which is 234 over 999, which simplifies or reduces to 26 over 111. So we're able to determine the fraction of a repeating decimal, which is a pretty neat thing that we're able to do. It's a neat little application of how to use a geometric series, of an infinite geometric series, to convert that repeating decimal to a fraction. So in this lesson, we worked with summation notation as it means to represent the sums of terms in any sequence. We learned how to use this notation to solve for the sum of a finite arithmetic sequence or a finite geometric sequence, and we evaluated infinite series and their limits and sums as we explored the convergence of geometric series. So you should be able to do all of those things. Use summation notation to represent the sums of sequences. You should be able to determine the sums of finite arithmetic and geometric sequences. You should be able to find the limit of a partial sum and determine the sum of an infinite geometric series.